Hello everybody, this is the last chapter which is called the first order circuits. The first order circuit is the circuits that has only capacitor or inductor. So for example, if you have a circuit like this and you have a capacitor, you have any source here, positive, negative, whatever. So this is what we call it here first order circuit. It has another capacitor, still has capacitor only, does not have capacitor and inductor together. If it has capacitor and inductor, it's called second order circuit. So if you have a circuit, for example, that has another capacitor like this, still this is a first order circuit. And today we'll talk about this. In chapter 6, we were able to solve a problem like this very easily. So for example, assume that if we have for example, the voltage here is 10 volt. For example, this is 10 volt DC. And this resistance is 10 ohm, for example. And you have this capacitor, whatever it is. So to solve this problem in chapter 6, you convert the capacitor to open circuit. You have a capacitor, you replace it by open circuit. Open circuit. And then after that, you calculate the voltage. Then the voltage here, when you replace these two capacitors by open circuit, you calculate the voltage between these 2 points. It's 10 volt because you don't have any circuit here. This is a resistor, and you have a voltage source, which is 10 volt. Okay, and you need to calculate the voltage between these 2 points. This circuit does not have any current or anything. In this case, the voltage between these 2 points is the same voltage across the source. It's 10 volt. So this is the voltage across the capacitor. Okay, but the question here is what? Does this capacitor or does this voltage reach 10 volt in no time? This is the question. In no time, no, this will not happen. The capacitor will act as open circuit, yes, but the final answer, this is the final answer. This is what we call it here, the final answer, the final voltage. Final voltage, or we call it DC voltage. DC voltage. So the DC voltage here is this 10 volt. This is a 10 volt. Okay, across the capacitor. But what will happen? Initially, if you imagine the capacitor does not have any voltage. So the voltage, the capacitor will not have any voltage across it. Zero. Okay, but when you connect it to the circuit, it will have 10 volt. What is in between? This is what is this chapter about. What is in between? How it look like in between? So I know that this capacitor has 0 voltage at the beginning, so it doesn't have any voltage. So imagine that you have only one capacitor here. So you don't need two capacitors to explain this. Imagine that you have this capacitor here. So this capacitor, if you connect this capacitor to this circuit, it doesn't have any voltage around it. So the voltage around it is 0. Okay, and now if you connect it to the circuit, I know that the voltage will be 10 volt because the capacitor is open circuit. Simply between 0 to 10, this is what we need to know, how it look like. And this is a first order circuit. Call it here, there's a transient or a space between 0 and 10. 0 and 10. And this is very similar to what? The capacitor is, as I said before, the capacitor is storing energy in terms of voltage. So the capacitor is acting as a voltage source. So actually you are charging the capacitor by voltage. And this is very similar to what? Similar to your cell phone. When you have a cell phone, and in cell phone, you are charging it. Okay, it is empty, doesn't have any power. And then you charge it, you put it on the charger for a while. It will charge from 0 voltage to whatever, for example, 9 volt, or I believe it is sometimes 9 volt, most of them. 9 volt, for example, maybe. Okay, so it takes some time, of course, to go from 0 to 9 volt for the cell phone. So we need to know how it look like in between. So for example, if you look at this slide here, this is a cell phone. The same phone is empty here, so you don't have any voltage. So the voltage here is 0 volt. Okay, so what you need to do is to connect it to the power, and then it will start charging until it reaches the maximum, which is here. This is the maximum. And if we compare this one with the previous example, then the voltage across the capacitor, the battery will be very similar to the capacitor. Initially it was 0, and then finally it was 10 volt. This was the previous example. So the capacitor is exactly the same like the battery in your cell phone. You are charging it, and if it is empty at the beginning, for example, maybe it is not empty. Sometimes you charge the cell phone when it is not empty. It's not completely 0. Maybe it has, for example, 1 volt, 2 volts, but it is still red. So you need to charge it. For example, start from 2, but after a while, you will reach the maximum, which is 10 volt, for example, here, or 9 volt, whatever your battery is. So this is what we need to understand. So how we know this relation? Like this is what we call it here. So where it is? Let me check. This is the equation here. Let me jump to this one and return back to the previous one. So this is the relation that tell us what is the voltage across the capacitor in case if you have a DC source connected to capacitor or circuit that has R and C. Okay, so this is how it look like. This is how it look like, the first equation. This one here. So what is the voltage across the capacitor? The voltage across the capacitor equal VCDC. VCDC, this is the DC voltage which we learned in chapter 6. Like in the first example which I gave you today, the voltage is 10 volt. I know that's 10 volt. So this is VCDC. Okay, this is VCDC. So what is VCDC? This is the voltage across the capacitor in case of DC, like in chapter 6. So you replace the capacitor by open circuit and then calculate the voltage between its two terminals. Second is the initial voltage. And the initial voltage should be given. So you don't have to calculate the initial voltage. Okay, the initial voltage is always given. I will tell you, okay, this, for example, I'm charging the cell phone and the cell phone was dead. Then the voltage is 0. The initial voltage is 0. Or, for example, the cell phone has 1 volt, for example, then the initial voltage is 1 volt. The cell phone has 2 volts, then the initial voltage is 2 volt. So this initial voltage should be given. You don't have to calculate it. Second one here, or third one, this is VCDC, the same one. And then time what? Between bracket here, you have e to the power of negative t. This is a time in seconds. Divided by what we call it here, tau. Tau is called the time constant. Let me write it here. It's called tau. T-A-U. Tau. So this is what we call it, tau, or time constant. Time constant. This is the time constant, tau. And what is tau? Tau equal R times C. R times C. How do you calculate it? C is a capacitance. We know this. C is a capacitance. R is the resistance between the two terminals of the capacitor. So if you have a capacitor like this, for example, this is a capacitor here. Okay. So you need to find the resistance between this A and this B. This is R. So it is R between A and B. So once you calculate this R, you multiply it by C, this will give you the time constant tau. So here you have how many parameters? Number one, you have the initial voltage. This is the one that you don't have to calculate it. Let me highlight it. So this one here, you don't have to calculate this one, the initial voltage. So you always start with this one here. Why? Because you don't have to do any effort here to do this one. It is, or it should be given. Second, you need to calculate the DC voltage. You need to calculate the DC voltage. Like in chapter 6, you remove the capacitor is open circuit, and then solve the circuit that you have. This is a DC voltage. And then next, you need to calculate tau. This tau is what is R times C. And R is the resistance between the two terminals of the capacitor. Here it is A and B, so you need to find the resistance, total resistance between A and B, then multiply it by C. When you multiply it by C, this will give you what we call it here tau. You substitute by VCDC, VC0, and tau, you will write the equation for the voltage. Okay, so this for the capacitor. For the inductor, it is very similar, but the inductor stores current, does not store voltage, so the relation will be for the current. So instead of voltage, you have current. So you see here for the capacitor, the current equal what? Equal ILDC. This is the first term here, ILDC. What is ILDC? This is the current in the inductor in case of DC. So again, this is similar to chapter 6. So you convert the capacitor, or replace the inductor, you replace the inductor by short circuit, and then calculate the current in this short circuit. This is ILDC. This is ILDC. Then again, the initial current in the inductor, this should be given. You don't have to calculate it. You don't have to calculate the initial current or the initial voltage. So you always start with this one, the initial voltage and the initial current. You don't have to calculate them. It should be given. Then you need to calculate tau. This is the time constant. The time constant here equal L divided by R. L is the inductance, and R is the resistance between the two terminals of the inductor. So it's very similar to this one, but here you have R times C. Here you have L divided by R. So R is the resistance between the two terminals of the inductor. So if this one is L, for example, so you need to calculate the resistance between these two terminals, A and B. This is R. So R, AB, this is the resistance that you use to calculate the tau, the time constant for the inductor circuit. Okay, so this is the main slide for this chapter. How do you calculate the current in the inductor, or how do you calculate the voltage in the capacitor? Okay, if we look at these two equations, okay, so you have here the initial voltage and you have the final voltage, which is the VCDC. Assume that T is, for example, is infinity. So you are charging a capacitor and for long time. So now if we look at this equation, let me erase everything. Erase all this. Okay. So now if you look at the first equation, and now assume that T is infinity. So now you are charging the capacitor for a long time. What happened? When T is infinity, this number is big. So you have e to the power of negative infinity. Infinity over tau is infinity, which is 0. When T is infinity, okay, so this term here is 0. Why? Because it is e to the power of negative infinity. That is 0. So this means that you cancel all of this. And now, what is the voltage across the capacitor? The voltage across the capacitor is a VCDC, which is the final voltage. And this is what I said before. Remember when I said you will charge the capacitor from 0 to 10. Finally, it will be 10. I know that it will be 10. Okay? As is proven here by this equation. But in between, this is what you need to know. So initially it was 0. Finally, it will be 10. Okay? So this is what is proven here. But this equation just show you the voltage across the capacitor in between. Exactly like when you charge a cell phone. When you charge a cell phone. And your cell phone, for example, is 10 volt. The battery of your cell phone is 10 volt. Okay? So you know, after, for example, 13 minutes, 30 minutes, or 1 hour, for example, you know that the voltage across your battery will be 10 volt. You know that. But in between, how it look like, this is what you need to know. So this equation will tell you how to calculate the voltage across your battery. Okay, but you know at the end it will be 10 volt, and it will remain 10 volt. So this is the job of these two equations.